Understanding causal graphs. This video is about directed acyclic graphs for causal inference, how to understand them, how to create them, and how to interpret them. First, what are directed acyclic graphs, or DAGs? DAGs are a graphical tool to represent relationships between anything. Causal DAGs are specifically a subset of DAGs which can help us understand how to design our studies, explain the methods that we're using, and figure out what surprising results might mean. Here's an example of a causal DAG where we have the summer or temperature represented by the sun with sunglasses on, ice cream consumption represented by the ice cream cone, and crime represented by this little burglar. This DAG shows us that increases in heat can cause both increased ice cream consumption and increased crime. But otherwise, there's no relationship between crime and ice cream, and we'll come back to this. A more common type of DAG you might see is one that uses words instead of pictures, and these are probably more appropriate for a scientific publication, but they're a lot less fun. So in this second DAG, we see randomization causing treatment, which causes some outcome, and then we have some other variable U, which is a cause in common between treatment and the outcome. So when should we use a causal DAG? Whenever we want to do any kind of research that involves a causal or etiologic question, a causal DAG is appropriate to use. So another time we might want to do this is if we're trying to figure out what systematic bias might exist in our study design and analysis, either before we create our study or afterwards when we're assessing it. If we're thinking about a causal or etiologic question, we probably want to think about confounding or selection bias. But even if we're thinking about a descriptive epidemiologic question, we could think about problems related to loss to follow-up or selection of our participants that makes in some way a bias appear in our study. In particular for causal questions, we can use the causal DAG to answer the question, is the causal effect of interest identifiable? That is, can we calculate it from the data that we have? We can also use causal DAGs to figure out the structure of the bias in terms of informing decisions about what analytic approach we should use. For example, if we've identified some confounders, this will tell us that we need to control for those in order to eliminate bias. On the other hand, we may discover that although we've identified several confounders, one of them is not in our data set, and a traditional method will not suffice for controlling for that confounding. Finally, we can use causal DAGs after we've conducted a study to think about how unique or unexpected results may have come about. And an example of where this was particularly useful is thinking through what we call the birth weight paradox, where when looking at low for birth weight infants, it appears that smoking is protective of harmful birth outcomes, even though smoking is actually a cause of these birth outcomes. This is a situation where drawing the DAG makes it easy to see that selecting on low birth weight babies is a collider and opens up a bias pathway. So causal DAGs can be used to interrogate whether the findings from your study really are likely to represent a true causal relationship or may arise from bias. And this can be from your own study, or it can be on a paper you're reading or another project that you're evaluating for someone else. In order for a graph to be a directed acyclic graph, there are three basic rules. The first one is pretty obvious, they must be graphs. The second one, also right in the name, they must be directed. And the third, again, in the name, they must be acyclic. So, that's a little bit tautological. What do these actually mean? Let's talk through those. So, what makes a graph? When we're talking about a directed acyclic graph, we want to have nodes, and those are the variables. So in this particular graph, we have a node that represents sleeping, a node that represents Santa Claus, and a node that represents presents. We also need edges connecting those nodes. And in this particular graph, we have 3 edges. Those edges are from sleeping to Santa, sleeping to presents, and Santa to presents. Note that those are all the possible edges we could have in this graph, and those edges are possible even if we don't think that there's a relationship there, and we'll talk more about this later. Obviously, that was a really oversimplified example. When we think about a really realistic directed acyclic graph for a real research question, these can get complicated pretty quickly. So looking at this DAG, think for a moment about what the elements of this DAG are. So we have nodes, and if you want to check your answer on how many you got, we have 9 of them. If you didn't get 9 when you were looking at this, go through and have another look at the graph. We also have edges. I'm not going to list them all because there are many of them. In this graph, we have 17 arrows on edges where we believe there may be a relationship. There are also edges where we haven't put an arrow. And so those are edges where we think there's no relationship. And we'll talk about this again more as well. The second major rule of directed acyclic graphs is that the edges must be directed. And so what this means is that we're not just talking about a line connecting 2 variables, we're talking about an arrow with an arrowhead at only one end of the arrow. And this arrowhead represents potential for causation that moves from the past to the present or from the present to the future, and the arrow indicates the direction of that causation in time. So in this particular picture, the heat in summer causes ice cream consumption to go up. The heat in summer causes crime to go up. We're not saying anything about whether crime affects summer or ice cream affects heat with these arrows. We're only talking about the effects of summer on those 2 variables. So in this graph, we have edges summer to ice cream and edges to summer to crime, and those are telling us about what we think is the cause and what we think could be the effect. Where we don't have an edge, we're assuming that there is no causal relationship. So for example, from ice cream to summer, we have no edge going that way, so no arrow from ice cream directed into the summer. And there we're saying that there is no causal effect of ice cream consumption on summer. You can't make summer come faster by eating ice cream. We're also saying there's no edge from crime to summer. So with no arrow that way, we're saying that crime doesn't cause summer, so you can't make summer come faster by robbing a bank. And we also have no edge either from ice cream to crime or crime to ice cream, representing that we don't believe that eating ice cream causes people to commit crimes, and we don't believe that committing crimes causes people to eat ice cream. In our realistic DAG, what the directed piece means is that we want to lay out the DAG according to the flow of time. So on this DAG, which is representing the relationship between asthma, smoking over a person's life, on the extreme left-hand side of the DAG, we want to put the parental variables because those happen the earliest in time. Whether your parent had asthma or whether your parent smokes is something that could have happened before your particular exposures. Then in the middle, we want to put the childhood exposures for the individual. So does this child have childhood asthma? Do they have underlying atopy? Do they have chronic bronchitis and poor lung function? We also can put other variables that are related to childhood, such as sex or SES, in the middle of this graph. And then finally, at the very right of the graph, we're going to put those downstream adult consequences, like does this person choose to smoke in their teen or adult years, and do they end up with asthma themselves as adults? So you can see how this fits the flow of time. The third rule is that DAGs must be acyclic, and that means that the future cannot cause the past. So in this graph right here, we have treatment at the top and some confounder at the bottom. And we're saying that that confounder, whatever it may be, for example, how serious your symptoms are, causes treatment decisions to be made, and that the treatment itself affects the value of that confounder. So this is a directed graph because we have single-headed arrows between each of the variables, but it's not a directed acyclic graph because it has a cycle. If we want to represent a cycle like this in a DAG, we can do it. The solution is that we have to break out separate nodes for the variables at each time. So if we want to capture a dynamic relationship, we have to break out each of these pieces. So here is an example where we've broken out those variables and actually even added a couple more. So starting on the left-hand side, we have, say, randomization. That determines your initial treatment. We have some baseline health status. So what are your symptoms at baseline? That's related to your symptoms during follow-up. And through your symptoms during follow-up, it's related to treatment at a later time point. Treatment that you get at baseline is related to your symptoms later at follow-up too. And then both treatment and symptoms could be related to some health status. And so you can see here now that we've taken that circle and we've broken it into a line. And so now we have a directed acyclic graph that tells us about a dynamic relationship as it happens over time. And I think it's important to note that this is how we experience time in the real world. We don't ever actually experience a cycle as a circle, because nothing in our future causes our past in our lives either. So it's really natural to think of it this way, and it's easy to say, okay, study visit 1, study visit 2, study visit 3, and the trick is just lining those all up in terms of which pieces we think cause which other pieces. So those were the rules for directed acyclic graph. If we want to make a causal directed acyclic graph, which is what we really want for causal inference, then we have to add a fourth basic rule. And this rule is that any common cause of any pair of variables already on the graph should be added to the graph. So what does that mean? Well, when we start off, our graph should have an exposure, an outcome, and any restrictions that are built into our study design. So for example, if we're doing a case control study and we're only including people who are eligible to be recruited as cases or controls, then that's a restriction in our study. On the other hand, if we're doing a study of dementia and we're only including women over the age of 65, then those are two restrictions on our study and we would need to put them in. Another possibility is that we're doing a longitudinal study and some people drop out before they're able to provide information on the outcome. In that case, loss to follow-up would be a restriction in our study. Once we have those three types of variables on our DAG, then we have to start thinking about what variables may be common causes of any of those. So let's take a look at an example. So if we wanted to think about the relationship in that bigger DAG we looked at between smoking and asthma, one of the things we say there is that parental asthma is a cause of parental smoking, and parental smoking is a cause of childhood asthma. Now, maybe this is what we think happens, or maybe it's not quite right. Parental smoking, if that's our exposure, and childhood asthma is our outcome, then we need to think about whether parental asthma is also a cause of childhood asthma. And so this might actually be a more appropriate conceptualization of the causal relationships, where parental asthma is a common cause of both. On the other hand, we may instead think that it's not that parental asthma directly causes a child to have asthma, but what's really going on is that there's a common cause of parental asthma and childhood asthma. And that might be, for example, a genetic predisposition to asthma. And so this might be actually a better graph that represents what we think is going on in terms of the causal relationships between these variables. And when we're drawing out a graph to design or analyze our study, it's really important that we think about this larger causal graph, even if we end up deciding that we have no way of getting data on genetics. We need to know that genetics belongs on that graph in order to evaluate the possibility for bias. So a couple of additional features of causal directed acyclic graphs that are important. And this is one that we've sort of hinted at, but directed edges encode causal assumptions. So what this means is that the lack of an arrow is a bigger assumption than the presence of an arrow. In the DAG here below, we're including arrows between sleeping and Santa, sleeping and presence, and Santa and presence. This DAG potentially represents what we think might be happening when we go to bed on Christmas Eve and wake up in the morning and see presents, but it makes no assumptions about whether or not Santa is actually the cause of presents, or whether, as my mom always told me, going to bed will make Santa show up. On the other hand, if we remove that arrow between Santa and presents, we're explicitly assuming that even if going to bed does make Santa show up, Santa is not the cause of the presents. It's actually going to sleep, which makes the presents show up as well. And so in this DAG, we're allowing the possibility that the presents show up because we went to sleep. We're allowing the possibility that Santa may show up if we go to sleep, but we're making a strong assumption of no causal relationship between Santa and the presents. So if we stayed up and Santa still came, he would not leave presents because Santa is not the reason that the presents are showing up. Okay, so the nodes contain information on the variables that we know about and the variables we don't know about. That's what the variables are. But they can also encode statistical or data restriction information. And we do that by putting a box around any node where we want to indicate that we're either going to restrict in the analysis or we're going to adjust statistically, restrict in the design or adjust statistically in the analysis. So in these three DAGs here, A and C in each DAG are not adjusted for or not restricted on. B is either adjusted or restricted or some combination of both. The box doesn't tell us what we're doing to B, it just tells us we're doing something to B. So now let's talk about how we can have variables and edges related in our DAGs. So the first and simplest type of relationship between variables and edges is what we call a chain. So here we have this little person exercising, an arrow from exercise to medication, and an arrow from medication to heart rate. So this chain implies the possibility of a causal relationship between exercise and the requirement to take medication, and between medication and heart rate. And importantly, this does not tell us about the magnitude or direction. So it's possible that exercise could reduce the need for medication. And then it's possible that reducing the need for medication could worsen an existing heart condition. It's also possible that reducing the need for medication could improve heart rate because perhaps the medication had an effect on heart rate as a side effect of whatever its primary treatment goal was. So we're not encoding any information about the direction of the relationships, just allowing the possibility that those causal relationships exist. The next type of scenario we can have is what we call a fork. So you can see here that at the sun, the arrows are forking, and one arrow is going forward to ice cream. The second arrow is going forward to crime. Forks like this can create the potential for spurious associations like confounding. And what this means is that if we were to just look in our data at the relationship between ice cream and crime, so comparing the expected rate of crime, if nobody eats ice cream with the expected rate of crime, if people are eating ice cream, if we just look at that in a crude association in our study, we'll see a relationship. That expected difference will not be zero. If we run a regression model where crime is our outcome or ice cream is and we put ice cream in our model, then we'll see a relationship. But that doesn't mean that ice cream causes crime. Instead, this fork is creating a spurious association, and to prevent it, we can either restrict on the fork. So that is, we can look only at ice cream and crime on days when the temperature is a particular level or in a particular range. For example, ice cream and crime on days when the temperature is above 100 degrees Fahrenheit or is between 75 and 80 degrees Fahrenheit. On the other hand, we can condition on the fork variable. So we could run a regression model where we include season as a term in our regression model. And when we do this, if this is the true causal DAG, we will expect to detect no association or no relationship between ice cream and crime, because our DAG here says that in the absence of that spurious relationship due to heat, there is no causal effect of ice cream on crime. The third type of relationship we can have between variables is what we call a collider. So a collider is a variable where two arrowheads meet. And it's important to remember that whether something is a chain, a collider, or a fork is what we call path dependent. So just because two arrowheads meet doesn't mean that this variable is always a collider. There may be another path where those two arrowheads chain or where those two arrows fork. So in this particular example, we have as our collider a wet sidewalk. And we have rain as a cause of that wet sidewalk. We also have watering the flowers as a cause of that wet sidewalk. If we just look for a statistical relationship between rain and no rain on watering the flowers, we will not find one under this DAG. So, this is something that, some people are happy to water their garden even when it's raining. And so we can't tell whether or not it's someone is out watering their flowers just by looking at the rain. On the other hand, if we condition on that collider, for example, we only look at the days when the sidewalk is dry, or only look at the days when the sidewalk is wet, then potentially knowing something about whether or not it's raining will tell us something about whether or not the person is watering the garden. So for example, if the sidewalk is wet and it's not raining, then somebody must have recently watered the garden. Otherwise, there's no explanation in our graph here for what could have happened. So this is where we create a spurious association by conditioning or restricting on the collider. Okay, so let's recap the basics of the DAGs. First, when we think about a DAG, causation flows in the direction of the arrows. On the other hand, association can flow in the reverse direction. If we have missing arrows, then we're assuming no causation. If we have two arrow tails meeting, then we're assuming that association can flow in both directions between those. And that's a fork situation where we can potentially have spurious confounding if we don't condition. If two arrowheads meet, then association is blocked between them. And if we restrict, we reverse the rules. So when we restrict and we have a fork, association is blocked. If we restrict and we have a collider, association is allowed. So let's go through next a few examples of some DAGs and what they might tell us about. So here we have an example of 3 different DAGs. The first one in the top left is depicting something we might see in an observational study. We have exercise, we have medication, and we have heart rate, and this is one we've seen before. In the bottom left, now we're adding on the possibility that actually, in order for this to be a causal DAG, there may be some variables that are common causes of exercise and medication usage, or of exercise and heart rate, or of medication usage and heart rate. And if any variables like that exist, then it's a potential that our observational study could have spurious confounding, or spurious association in it due to confounding. We would need to identify those variables and either condition on them or control from them. On the right-hand side, we see one way of solving that problem. And that way is to say, well, okay, maybe we don't think there's any common causes of exercise and heart rate, but we're going to randomize treatment with the medication. When we do that, we can now easily see what's going on in terms of randomization to treatment and the medication. And this solves some of the confounding problem, but you can see it doesn't necessarily solve all of it. So now I want to go through some kind of common structures and how they might look in a DAG. So the first one I want to talk about is what we call reverse causation. Reverse causation comes about when something that we think that we have found an exposure that is a cause of some outcome, but really we have basically confounding by pre-existing undiagnosed disease. So in this DAG, we represent that for the problem of the relationship between physical activity and colon cancer. So here, our variable A is a little individual doing physical activity. That's our exposure of interest. Y is an individual with colon cancer. That's our outcome of interest. And what we see in this particular graph is that U is unmeasured preclinical disease. That's a potential cause of exercise. That is, if people are already sick, they may stop exercising. On the other hand, preclinical disease could also affect someone's weight, especially with colon cancer. We know that preclinical disease can lead to weight loss often before people are diagnosed. And so now weight may be a marker of colon cancer because of this pathway. So if that's the pathway that exists, that there's any relationship between weight and colon cancer, if we think about just the relationship of exercise on colon cancer, weight here would be a confounder because of this relationship through preclinical disease. If we control for weight, or maybe BMI as a proxy, this would allow us to assess independently the relationship of exercise on preclinical disease. On the other hand, we also expect preclinical disease may be a direct cause of later diagnosis rather than operating through weight loss as a signal that someone should go and get diagnosed. And if that's the case, that we have an arrow from U directly to Y, then conditioning on L is not going to solve our problems here. Another common bias we see is selection bias, and in the setting of a case control study, that's often called Bergson's bias. What happens is we select our cases from the hospital, and we select our controls also from the hospital, but who are in the hospital for a different reason. So you can see here that being a case is or not is associated with being in the hospital. Having this other condition, which we're using to sample our controls, is also a cause of being in the hospital. And what we want to know is whether there's an association between medication and our index exposure, or our index outcome of this case. But if the medication usage is, for example, related to an exposure that causes our other outcome, what we see is that by conditioning on hospital, we can create an association between being a case, being in the hospital. That's now an open collider back to the other medical condition, whatever the cause of that medical condition was, which here, say it's people who've shown up for dehydration. They're dehydrated because they were drinking, and they're drinking because they're less likely to be taking this medication, which has advice not to drink. If that's true, then even if this medication has nothing to do with the outcome that we're primarily interested in, we may see a relationship due to this selection bias. Another thing that's useful in DAGs is to think about confounding with a time-varying treatment. So again, we want our DAG to be acyclic. This means if we have multiple treatments, we're going to open that DAG up and show it on a long line rather than a circle. So we have treatment at time 1 and treatment at time 2. Time-varying treatments are a problem whenever the treatment affects a variable like viral load during follow-up here, and that variable also affects future treatment. And the problem arises if there's any common cause between that variable and the outcome, because that makes LT a collider. And now, even if treatment were independent of the outcome, so long as treatment affects viral load, then and we're going to condition on viral load because it affects future treatment, then we have a potential induced association here. If we use a typical traditional regression model where we just put LT in the model, that's like opening up this collider, and that's a problem. So traditional methods will induce selection bias here. Instead, we can use an alternative method, something like IPW or the G formula. When we do that, instead of conditioning on viral load, we actually remove the arrows into it in a way that makes this no longer a problem. And that is a story for another video, but you can just trust me on that for now. Okay, another bias that's really common is something called the healthy worker bias. And this is a problem where if we want to look at an occupational exposure and how it impacts survival or healthcare over time. So here, A, beryllium exposure is our exposure of interest, and Y, survival, is our outcome of interest. In order to study that, we often have to condition on being at work. Because we're interested in occupational exposures, the exposure is only defined for those people who are getting exposed at work, which means they have to be at work in order to get exposed. However, the things that lead someone to be at work may be related to things that lead them to be at work in an industry that causes them to get this exposure. So there may be economic pressures which force them to take a job that has a potentially hazardous exposure and to remain at that job no matter what. It's also possible that their underlying health may affect whether or not they show up at work. So, for example, if they get diagnosed with some serious medical condition, even if that medical condition is a result of the beryllium exposure, that may cause them to not come to work, which would mean they're not in our survival analysis. And because of that, we might fail to detect these individuals. So if the underlying health is a cause of being at work and some relationship between underlying health and survival exists, for example, the actual health of this individual, now we can have, you see here, a pretty complicated, but a path between survival and the exposure that doesn't require any actual causal effect of this exposure on this outcome. I'm not saying that there is no relationship here. This is just a purely made up example. Colliders are a little bit tricky because it's not just the collider itself that we need to focus on. So I also want to warn you about conditioning on the descendant of a collider. So here we're just going back to the simple text-based directed acyclic graph. If we have an exposure and an outcome, there's some confounder, but collider between them, say Z. If we need to condition on something that's caused by Z, even if that selection variable is not a collider itself, the fact that it's the descendant of Z, which is a collider, will cause the collider to be partially open and create a spurious association between the exposure and the outcome. So when we're looking for colliders in our graph, we have to look not only for colliders that are conditioned on directly, but colliders where their descendant is conditioned on. And this can be really tricky for evaluating a DAG. Colliders are also nasty because they represent a possible place where a pre-treatment covariate can cause bias when we condition on it. And a lot of people have this idea that anything that happens before our exposure or treatment can be thrown into a model without harm, that we don't need to worry about conditioning on anything pre-treatment. It's either a confounder or it's not, and conditioning on it will help. That's not true because of something called M-bias. M-bias, if you sort of turn your head on the side, you'll see this is a little bit the shape of an M. I kind of wish it was called E-bias, both for Ellie and because it looks much more like an E to me, but I don't get to decide. So M-bias is what happens when you condition on a variable that's not actually a confounder, but is caused by a variable that's also a prognostic factor for the outcome and by a variable that's also an exposure determinant. And if you don't have that prognostic factor or that exposure determinant in your data, conditioning on this measured covariate by adjusting for it in the analysis or by selecting on it in your study design will open a collider that actually creates more bias than if you had just ignored that covariate in the first place. So this is a pretty weird type of bias, and it takes some thinking through. So I'm going to talk through a couple of examples of it. The first example we have here on the left is an example where we maybe want to look at the question, when an individual dies, is their spouse more likely to die within a short period of time than if that person hadn't died? i.e., does the death of one spouse cause the death of the other spouse? When we do this, we're kind of implicitly conditioning on marriage between these individuals because they're spouses. And so we've said, okay, these individuals have to be married. But being married isn't really a confounder for death for either of these individuals. And so it's not really something we would have liked to adjust for necessarily. It's also the case that there are certain things about the individuals who get married that cause them to get married in the first place. And if any of those things are prognostic factors and for the outcome, such as, for example, the education level of the second spouse, or predictors of the exposures, such as the education level of the index spouse, we can potentially create an M-bias pathway that would be opened by restricting to married individuals. So that one is a little bit hard to wrap your head around, although I think it's something that likely happens a lot when we look at married couples. But the example on the right gives us another way of thinking about it. So here we want to know, does the high school you go to affect your score on a high school standardized test? So our exposure is high school attended, our outcome is high school test score. It's really common in these types of educational analyses to control for middle school test scores. And the idea is somebody who tests well in middle school will test well in high school. And so maybe that's a confounder. And if middle school test scores do have an impact on which high school you attend, it is possible that it's a confounder. But for now, let's assume that there's no relationship between middle school test scores and which high school you attend. In that case, middle school test scores would not be a confounder, and we'd need to start thinking about what else could be going on. One possibility is that there's actually some underlying concept of ability to take tests, and that people who are high ability individuals do better on middle school tests and high school tests. So unmeasured ability is a prognostic factor for high school tests, and it's also a cause of middle school test score. Another thing that we might need to think about is that individuals who live further from their middle school may also live further from their high school. And if you have a long distance to commute to school, you may show up to school more tired, you may have less time to do homework, and you may overall perform more poorly on middle school test scores. And so now we have this variable distance to school, which is a predictor of middle school test scores and a prognostic factor of high school attended, because where you live determines what schools you might be eligible to go to. So in this case, now conditioning on middle school test scores could open up a collider that would make high school attended look like it's predictive of high school test score, even if it's actually not. Okay, so that was a lot of theory. I want to talk a little bit about using DAGs in applied research. How do you actually go about doing this? So you want to start with your exposure or exposures if you're thinking about a time-varying setting or a multiple intervention. Your outcome or outcomes, again, if you're thinking of a single outcome or an outcome measured at multiple time points, or maybe two different outcomes like progression of the disease and survival. And then any restriction criteria that you have to include based on your study design. Next, you want to add all of the known and measured common causes of each pair of these, even if you're not sure of a causal relationship. And so you only want to exclude things where you know for sure that there is no arrow between any two variables on your DAG. If there's an arrow, possibly an arrow for one variable, that's okay. You're looking for things that have arrows of two variables. Next, you want to consider unknown variables and maybe add some placeholders for them. So there may be things that you know about but haven't measured, or there may be things that you suspect might exist but you don't really know how to conceptualize them. And you can think of this like that unmeasured ability variable we just talked about in the last graph. We don't necessarily know what that is, we're not necessarily sure how to measure it, but it still could be causing a problem for our analysis. And so you want to put those on as well. Once you've drawn out all of the nodes and arrows, you want to check for open paths and identify how to block them. And so as a reminder, any path is open if it's a chain or a fork and there's no conditioning on it, i.e. no restriction and you haven't conditioned in your analysis. Or it's open if there's a collider that's restricted on or conditioned on, or the descendant of a collider that's restricted on or conditioned on. Closed paths are the opposite of those. And so when you're thinking about how to close paths, you want to think about, is there anywhere along that path that you could condition or restrict that would help close up that path? And once the path is closed at one node, you don't necessarily need to worry about any other nodes along those paths. And as a reminder, we're looking specifically for paths that connect the exposure to the outcome and not through the causal mechanism that we're interested in. There are some tools like daggity.com that can help with this. And that can be really useful. It doesn't draw the prettiest DAGs, but it can be useful for checking your assumptions about whether or not your analysis should proceed and how. And then I want to end with a couple of limitations of DAGs. So one of the things I talked about was that the DAGs do not incorporate the strength or direction of the relationship. So we don't know if the cause is making the effect more or less common. We don't know if it's more of the cause or less of the cause that's creating the effect. It's also not easy to depict effect modification. And so there's kind of different schools of thought around this. In general, anything that's also a cause of the outcome of interest is a potential effect modifier, but there's not really a good way to show that something is not an effect modifier. The last thing is that it's really difficult to know when to stop building out the DAG. As I said, you want to add any variable that's a common cause of two or more things that are already on your DAG, but at some point, you have to stop. Everything, there's kind of layers, you can build it out. At some point, you have to decide when to stop. And that can be a little bit challenging. Usually we stop based on where we have data and kind of hope for the best. So that's everything that I want to talk to you about DAGs. This gives you an overview of the basic rules and concepts, as well as how to use them and how to build them. And I hope that this was helpful for you. And thank you for listening.